Hey guys, as you can see, I'm recording from a new place. Welcome to my home. I am currently sitting on the couch. I may not always record from here, but I said, you know what? I want to be comfortable. We are going to a new chapter. We're going to chapter 20. We just finished chapter 15, and we're going to jump forward because we really only have time for one or two more chapters, and I would like to have us do a little bit on electricity. I want to teach you guys a little bit about electricity. So my plan is if we can fit two chapters in, we'll be doing chapter 20 and 22. All right, so chapter 20 is pretty quick. Let's review from chemistry. You guys remember what the structure of an atom is. If you remember, an atom would look like this. I can draw it here. Um, Protons in the nucleus and neutrons in the nucleus. So this is protons. Proton is P positive, P with a positive sign. Neutron is N with a zero. And then on the outside you have electrons orbiting around the nucleus, right? So this would be, so you have protons and neutrons in the nucleus and electrons orbiting around. In any normal circumstances, there are the same number of protons, which are positive. There are electrons, giving it a neutral overall state because the pluses are the same as the minuses. But in electricity, we talk about the movement of electrons. The first word you come across in this chapter is called electrostatics. And electrostatics is a study of electric charges that can be collected and held in one place. And so we talk about a charge. When we talk about a charge, we're referring to usually the movement of electrons. Charge, as we're going to see, is the unit is lowercase. I mean, the letter that we use to abbreviate it is lowercase q for charge. But we'll come back to that. Let's talk about how these things work. If you've ever had, like, as a book talks about on page 542, if you've ever had like a balloon rub, somebody rub something on the ground or rub a balloon on something and stick it to you, what's happening is there must be some sort of force because we know there's a force of gravity that pulls the balloon down to Earth. Well, there must be some force pulling the balloon onto yourself, overcoming gravity. And that's what we're going to talk about, electrostatic force. Um, you're going to learn this chapter that like charges repel one another and opposite charges attract. So in that situation of the atom, we have a positive proton and a negative electron. A little side note that's not important for this chapter, but it's really interesting that you see protons are stuck together in the nucleus. So we know that there's an additional force in addition to that because obviously pluses don't want to be next to one another. But we have, let's see, what do I want to cover here? I want to talk about the movement of electrons. So how it works is that the electrons are, coming out from the nucleus and everything, but there are certain electrons in the structure of the atom that are called free electrons. The free electrons are ones that are able to move. They're able to move throughout. They can be passed from atom to atom to atom, or even from substance to substance. These are called free electrons. These are the valence electrons that you guys would have studied last year. The valence electrons that can be that can be united in some kind of chemical reaction. You guys remember doing like Bohr models or electron configuration models or whatever, where you have these valence electrons um, connecting with different things in different ways, and those valence electrons, free electrons, can actually flow from atom to atom to atom. They can be passed from atom to atom, and what determines how easily they're passed is the material that they are going through. If they are going through what's called a conductor, it means that those free electrons, the valence electrons, the free electrons can be passed very easily from atom to atom to atom. If it's an insulator, so you've heard of conductor and insulator before. If it's an insulator, that means that the electrons do not move easily through that object. So for instance, a good conductor is copper. Copper is used for electricity. What that means is that those electrons can fly through with little to no resistance. A good insulator would be something like cloth or rubber or wood. Those things do not allow electrons to flow through very easily, and which means they it's almost like, if you can picture it, those electrons getting kind of stuck in molasses. That's what an insulator would do. It would not allow them to pass through easily. Now that's the key. It might be tempting to say insulators do not allow electricity to flow. That's not necessarily the case. They just make it very, very hard for the electricity to flow. Now, what determines a conductor or an insulator? It depends on the atomic structure. It's not like something like if it has this or if it has that, it's a conductor or insulator. It just depends on its atomic structure. From that, we know almost all metals are good conductors of electricity, and we know a lot of different insulators as well. There's a little list that you'll need to know on page 544, which is on the first paragraph of the conductors and insulators section. It says insulators. It lists insulators: glass, dry wood, most plastics, cloth, and dry air are very good insulators. Okay? And it talks about conductors as where is it? In that same paragraph somewhere. Well, anyway, I want you to know that. So let's go through. You're gonna have to during the test, you're gonna have to tell me what some examples of conductors and insulators, or if I give you examples, you're gonna have to tell me whether it's a conductor or an insulator. Glass. Glass is kind of a tricky one because sometimes it can be easiest to picture a conductor and insulator as heat because we experience heat very often, and a lot of times the conductors and insulators carry over between heat and electricity. For instance, aluminum or steel is a good conductor of electricity and also a good conductor of heat, right? So they're both. Or rubber. Rubber is not a good conductor of heat, and it's not a good conductor of electricity. However, glass is one of those ones that's a little different. Glass can conduct heat very well. Like you put, a glass bottle in a fire and you're touching it, all of a sudden it burns you. But glass is not a good conductor of electricity. Dry wood, and it says dry air. Now it's interesting to find out. So dry wood and dry air. The dry air, you know what? Let me come back to. I really thought they had a part that talked about conductors, but water. Let's come back to let's deal with water. Now, if I were to ask you, is water a conductor or an insulator? You would say, interesting. So the answer is that water could be both. Water, as we tend to, and we think of water as a really good conductor because we hear about, everybody talking about if you're in the pool and you're swimming and there's a lightning storm, get out because you could get electrocuted. We hear people talk about, anytime you're anywhere near the water, it's very dangerous. Well, what that means, what the reason is, it's not necessarily because of the water. It's because of the little inconsistencies and little particles in the water that make it a good conductor. Those little particles in the water can conduct electricity well, which means the water itself, that water will conduct electricity. If you were to have a completely purified water, like distilled water, it is actually a good insulator. Electricity does not flow well through distilled water. So one of those things depends. So we talk about dry air. Dry air does not have a lot of water in it. It's not very humid. It's an insulator. But if you start bringing water vapor into the air, that also will bring little imperfections with it, and now it becomes a good conductor. Um, when we charge something, talk a little bit more about charging things. You can charge in two ways. I might be getting ahead of myself, but that's all right. You can charge in two ways: charging by conduction and charging by induction. We'll deal with just conduction today. Conduction is when you are in contact with something, and I'm kind of jumping around a little bit, so don't worry about following along in your book. Charging by conduction is when you are physically touching the object. For instance, if you take something and rub it against something else, and like that balloon, you rub that balloon against carpet or whatever, and it becomes charged, that's conduction because it's in contact. Charging by induction is when you just bring something near, because charges can work over a distance. But I'm going to deal with charging by conduction now. What happens is when you rub two things together and they become charged, are these free electrons that I discussed before are jumping from one object to another. The classic analogy that is used in physics classrooms is like a glass rod and a piece of steel wool. If you rub a piece of steel wool on a glass rod, electrons will jump from the glass rod into the piece of wool. And why is that? So the question is, what determines what will jump from where? Okay. And it's something called the triboelectric scale. I am going to actually, I wonder if I can show you guys. I'm just doing a video right now. I'm not doing screenshotting my screen, so it's not necessarily the easiest thing. But let me see if I can. I will post this triboelectric charge, and maybe I'll take a picture right now and show you. Get like double screens going. My phone right here. I'm sure all the other teachers would have been doing screen grabs by now, but I'm going to show you like this. Get away. Oh, that didn't come up. All right, let's do this. This is going to be such a bad video. All right, let's do this. Ready? This is what a typical triboelectric series would look like. All right, so can you see that? It stinks. I was hoping it would be able to be seen. Let's go like this. Does that help? There we go. All right, good. Oh, come on. Ready? I'll do it this way. And can you see it? Oh, why won't it be able to be seen? Oh, I know why. I know why. Nope, still didn't help. Anyway, I'll just post it. Look at the triboelectric series that I posted, because I will post it, and you'll see that it says positive is on the top, negative's on the bottom. Positive's red, negative's blue. And you see something like air, human body, glass, nylon, wool. That's at the top. And now the bottom, negative, is vinyl, silicon, Teflon. That's what's going to happen in these interactions. What it means to be positive is it means it loses electrons, because think about it, an electron is a negative charge, and as the electron leaves, you're bringing out negatives. You're having negatives leave. So if I have like 10 negatives and 10 positives, and I get rid of 3 of those negatives, now I have 7 negatives and 10 positives. I have an excess of positive charges. And so the overall charge of the object would be positively charged. If I have 10 negatives and 10 positives, and all of a sudden I gain 3 electrons, now I have 13 negatives and 10 positives. And so now I have an overall negative charge that the object is. So it's kind of counterintuitive at first. When you gain electrons, you are more negative. When you lose electrons, you're more positive. So here in this triboelectric series, when you see objects that are more positive in the triboelectric series, that means they are losing electrons. So when in contact with something lower on the scale, so something like the human body, for instance, the human body would lose electrons when it came in contact with cotton, which is lower on the triboelectric series. That so if you were to take like some sort of cotton and rub it on your human hair or something like that, then you would lose electrons out of the hair onto the cloth. And so that's kind of how the triboelectric series works. And hopefully you're looking at it, because hopefully I remember to post it. So that's about it for today. Let me have you guys there's no real math in this part of the chapter, but let's see. Let's actually have no homework tonight, so make sure you guys watch this video. And that's it. All right, bye.